All right, our next couple topics are going to focus specifically on limiting and excess reactants, what we call fractional conversion, and then we're going to move on to extent of reaction in the next video. So the first thing that we want to talk about is what's called a stoichiometric proportion, and that's the ratio that's present in reality. This is the stoichiometric ratio of a balanced reaction. So in chemistry, you probably learned that all of our reactions need to be balanced, but the truth is that in the real world, they're not going to be perfectly balanced. Things are going to be there in fractions. We're going to exhaust certain reactants before we exhaust another. We're going to create a certain amount of products, and they may not be in the specific stoichiometric ratio. So the stoichiometric proportion is the ratio that's present in reality. The stoichiometric ratio of a balanced reaction is slightly different. So for example, if we have that example that we've been using, 2SO2 plus O2 plus 2SO3, if the reaction proceeds to completion for this one, all of the products are going to be, all the reactants are going to be consumed. So make sure you change that word in your notes. All reactants are consumed. In this reaction, if we have everything present in the stoichiometric ratio and it's balanced, then there's no limiting reactant. But the reality is that most likely we're going to have more oxygen or more SO2 because real world systems are just too complicated. So in that case, we'd use the term limiting reactant. That's basically tells us which reactant is consumed first if the reaction is proceeding to completion. And then the excess reactant is just the other reactants there. So the limiting reactant is the one that we're always going to care about for chemical processes because that's the one that disappears first in the reactions. So a reactant is going to be limiting if it's present in less than its stoichiometric proportion relative to other reactants. So say for example, with this example above, 2SO2 and 1O2, if we only have 1.5 moles of SO2, then that component is going to be the limiting reactant because it's present in less than its stoichiometric proportion, which is 2. If all reactants are present in their stoichiometric proportion, no reactant is limiting. But most of the time, we're going to have to find a limiting reactant when we do our balances. So let's talk about a concept called fractional excess. So if we have a limiting reactant, that means something is in excess. That means we have more than we need in order to consume all that reactant. So we're going to define two terms. We're going to say the moles of A, and A is a species. The moles of A in a feed is this component here, N sub A sub feed, is the number of moles of an excess reactant A that's fed to a unit. And then N sub A sub stoich is going to be the stoichiometric requirement of A. So that would be the amount that's needed to react completely with the limiting reactant. So we define something called the fractional excess of A as whatever's in the feed minus the stoichiometric amount divided by the stoichiometric amount. So it's a fractional component in the system. Oops, went a little quick there. So if you need to go back in the video, go ahead and go back and pause. So we're going to go over a quick example, and this is called hydrogenation of acetylene, and we're going to form ethane. So this is the reaction up top. This is a balanced reaction, or is it? That's a good question, right? Sometimes we might need to think about, do we need to balance this reaction? Let's suppose that we're feeding 20 kilomoles per hour of C2H2 and 50 kilomoles per hour of H2 fed to the unit. Well, the stoichiometric ratio of C2H2 to H2 is 1 to 2. So when I kind of said, well, is it balanced? That's because, let me grab my laser pointer, this needs a 2 in front of it to be balanced in order for our reaction to occur. So that's where this is coming from. So for every 1 mole of C2H2 that's consumed, we consume 2 moles of H2. So if we look at the metrics that were given, 20 kilomoles per hour of C2H2 to 50 kilomoles per hour of H2, we have a stoichiometric ratio of 1 to 2.5. So that's not the same as what's going on in the stoichiometric proportion. So as a result, that means that H2 is fed in a greater proportion to C2H2 than we expect to see based on stoichiometry. That means that we are going to get rid of C2H2 faster, and that means that C2H2 must be the limiting reactant in this particular example. If we wanted to say, well, how much fractional excess of H2 do we have? We would take 50 kilomoles per hour, which is the amount that's being fed of H2, and we'd subtract the amount that's there in the stoichiometric proportion. So there's 2 in front of that H2 if we balance the reaction, times the 20 divided by the 2 times the 20. So that's going to give us 25%. So we have a 25% excess of H2 in our feed. In the real world, our chemical reactions are not instantaneous. So as a result, it's not normally practical to design a reactor for complete conversion of a chemical reactant. It's just not going to happen. In the real world, there's too many confounding factors, too many limiting factors. So normally we'll use some kind of a separation process at the effluent in order to do a little bit more of that chemical processing. So we had fractional excess, but we also have a term called fractional conversion. So fractional conversion refers to the number of moles fed divided by the number of moles reacted. And then you can have what's called the fraction unreacted, which is 1 minus the fractional conversion. And then if we want a percent, we can multiply by 100%. So this is different than fractional excess. This is fractional conversion. So that's slightly different and a different term we're going to use. So let's do an example. If we take 20 moles per minute of a reactant and feed it, and we have an 80% conversion occurring, then that means that the moles that we reacted is 80% of that 20 moles per minute. So that means 16 moles has been reacted of whatever the reactant is. That means 4 moles per minute has been unreacted in the system. And these are going to start to become important to us as we do mass balance equations, because we're going to have consumption, generation, and amount reacted in the system. So we're going to want to make sure that we understand limiting reactant and how much conversion has happened in systems. That's going to start to become really important for us. The last thing that I want to do is just go through a really quick example. So if we take that same equation and we balance it this time and we put that 2 in front of the H2, if we feed a system 20 moles of C2H2 and 50 moles of H2, and we start off with 50 moles of C2H6 at the start of our reaction, we want to know how much of each species is present after 30 moles of H2 has reacted. So to do this example, first we would say, well, we have 50 moles of H2 fed, and we're going to subtract the 30 moles that are reacted. And that's going to give us 20 moles of H2 still remaining in the system. Then we can say, well, if 30 moles of H2 react, then 15 moles of C2H2 must react because it's present in half the stoichiometric ratio of H2. So only 15 moles of C2H2 are going to react. If we then take the 20 moles of C2H2 that are fed and subtract the number reacted, we'll find that we only have 5 moles of C2H2 remaining in the system. If 30 moles of H2 are going to react, 1 mole of C2H2 is produced because there's a 1 in front of it. So 15 moles of C2H2 are going to be generated for every 1 mole of H2 that reacts. And so what that means is if we started out with 50 moles, we have generated, which is why there's a plus sign here, we've generated an additional 15 moles, which means that we have 65 moles of C2H2 at the end. So make sure that this example makes sense to you as you think through it. A lot of this may be intuitive if chemistry is really, really fresh for you, but it might not be. So just take the second to make sure that this is really, really solid so that going forward we're able to start to work with generation and consumption in our mass balances.